All right, so question one asks about a hotel. This is the hotel problem. Essentially saying that a hotel rents out 100 rooms each night when the room is $6 per night. And the data suggests for each $3 increase in price, they'll rent out 2 less rooms. So let's go ahead and make a little table here for the amount of room that they have and the price of the room. So the rooms and then the price. It says that at 100 rooms, the price looks like it's going to be 60 per night per room. And then it says every $3 increase in price, so we'll write a couple $3 increases in price. So we're at 63 and 66. It looks like they rent out 2 less rooms. So it looks like 98 and 96. We can make like a general formula for both of these, where we can say this is going to be 60 plus 3x here, and this is going to be 100 minus 2x. Now we're looking for the maximum revenue, right? So A is asking for the price of the room that will maximize the revenue, and then B is asking about the maximum revenue in general. And if you guys want to go ahead and keep dropping your questions in chat, I'm going to go ahead and try to go from the top to bottom. So I'm just going to read like all the way down, starting from the top, and then that's going to be the order of the questions I tackle. So our revenue function is actually going to be, as far as R of X is going to be, and this is like rooms instead of just big R, and this is price. It's going to be the number of rooms we have times the price of those rooms. In this case, as a general formula of X will be 100 minus 2x times 60 plus 3x. Cool. And then we want to maximize this function. So let's go ahead and get this in terms of a polynomial. So this will be, oh, let me scroll my chat down as well. Okay. This will be 6,000 plus x. Oh, sorry, it's not true. 6,000 plus, we have 300x minus 120x minus 6x squared, which is really going to be equal to 6,000 plus 180x minus 6x squared. Okay. And then to derive this, we're going to get that r prime of x is going to be equal to 180 minus 12x. The reason why we're deriving this is in order to find the maximum of any given function, which in this case the revenue function, we need to derive it and then set it equal to 0. So we're going to set this equal to 0, and we're going to get that 180 is equal to 12x, and then we'll divide by 12 on both sides, and that should give us mental math 15, right? Yeah, 15. X is equal to 15. That means we can find the rooms and the price. So we know that 100 minus, so for rooms, is going to be 100 minus 30 or 70, and the price is going to be 60 plus 3 times 15, which is 45, and it's going to be 115. Oh, sorry, 105. And then we can multiply these together to get the final price. So 75 times 70 times 105 should be what, 73.50. So maximum revenue is going to be 73.50. And then I believe the other part of the question actually asks about the price of the room that will increase revenue, and that will be this piece right here. So these will be your two answers. This will be answer to A, and this will be answer to B. Cool. Okay, so a fence must be built to enclose a rectangular area of 20,000 feet. So let's go ahead and just draw that out right here. It's a rectangular area. Okay. And then the fencing material costs $2.50 per foot of the sides facing north and south, and $3.20 per foot for the other two sides. Let's find the cost that is the least expensive fence. So first of all, what do we know? We know that these side lengths, we can represent this as X, or let's do this width and length, right? So we have a width and we have a length. This will also be width and this will also be length. We know that the area of this needs to be width times length. And it's going to be equal to, they give it to us, 20,000. And then we know that the price of this is a function of width and length. Is going to be equal to the north and south sides. It says $2.50 per foot for the north and south sides. So we have $2.50 per length here and $2.50 per length here. So really what it's going to be the rate, 2.5, times how much we have of it, which is 2 times length, right? Because we have one for the top and bottom. And we can add that to the same principle over here, which is just 3.2 times 2W. Okay, I'm going to solve for W here. But in order to get this into a form of just W and get rid of the L, we need to substitute it from something. And this is where we look at our constraint function right here, which is just saying that the area has to be 20,000. So this gives us then that W, or our width, is going to be equal to 20,000 over our length. And we can plug that back into our original equation. So, oh, sorry, we want to do this the other way around. Length is equal to 20,000 over width. It doesn't really matter which way you do it. You can really do either, but because I've already stated this P or W, then I'm just going to use it. Okay, so we'll substitute. We'll divide both sides by width, and then we get length is equal to 20,000 over width. So we're going to plug that back in. We get, over here, we get 2.5 times 2 times this length, which is 20,000 over width. And then we have plus, I'd argue, 6.4 W. And then we can kind of do a little bit of simplification here. And we get 5 times 20,000 is 100,000. So we have 100,000 over W plus 6.4 W. We're going to derive this to maximize it. Once again, we have to derive it set it equal to 0. So we have P prime of W, or the derivative of W, will be negative 100,000 over W squared plus 6.4. We're going to set this equal to 0 now. We're going to solve just like that. We're going to add this to the other side. So we're going to get 6.4 is equal to 100,000 over W squared. We're going to multiply W squared by both sides. We're going to get 6.4 W squared is equal to 100,000. And then W squared is going to be equal to, well, we can just say, W squared is going to be equal to 100,000 over 6.4. And then W is going to be equal to the square root of whatever that number is. Let me open up Decimal real fast so I can find out the answer to that. Over 6.4. And this ends up being 100 plus or minus 125. We can ignore the negative solution because we know that width is a measurement and therefore cannot be negative. You cannot have a negative width, right? So width is going to be 125. And then we can plug it right back into this equation to get our length, right? So if width is going to be 125, then we'll plug it back into length is equal to 100,000, or sorry, 20,000 over width, which is 125. And then we could say 20,000 over 125 should be 160. So the dimensions of my fence that will maximize, that will minimize the cost, sorry, with the given constraint of the area being 20,000 will be the width being 125 and the length being 160. These will all be feet, by the way. Cool. Any questions here before we move on? Okay. All right, so it says consider the two functions. Y is equal to 9 and, oh, wow, that was really bad. And y is equal to the square root of x on the, okay, it says first for A, it wants us to sketch, hold on. There we go. Wants us to sketch a graph on the region bounded by the first two functions. I'm not really going to go into why this is, but the graph is going to look something like this, where this is our line at y equals 9, and this is going to be our y equals x squared, and then these are going to collide at 81, x is equal to 81. So our bounds are going to be from 0 to 81. And then this is going to be the region that we're going to try to integrate on. Okay, so this is going to be our graph. Oh, it actually says specifically, actually this is great, that we want it to be in the first quadrant. So it's really going to be looking for something like this, where we have our line at y equals 9, and then our y equals x squared graph. If you're unsure about how to get this, I take plot a few points and then try to connect them with the line.
Why is start from 0?
Why do I start at 0?
Yeah.
Because it asks for the first quadrant. Also, you can't have negative inputs for the square root of x.
Oh. Okay.
Otherwise, you get imaginary solutions for y. Yeah, of course.
And then I got a question.
What's up?
How do you know, like, you have to shade the upper portion, not the bottom portion?
Because you want the area between the curves. This area is just the area between the top curve and the bottom region. But because it asks you to, it says to find the region bounded between the two functions. Does that make sense? I feel like that's relatively self-explanatory, but like,
yeah,
you usually will want them to be in between the curves. Okay, cool. And then it says actually in the note, it says it should be the area above the square root function and below the line, which is exactly what we shaded. Okay, and now it asks us to calculate the area of the region. I'm going to spare you some time because this y equals 9 is on top and this y equals square root of x is on the bottom. The integral, we've already found our bounds to be 81 because this is where they both collide, right? From 0 to 81 of 9 minus the square root of x dx. So this is how we're going to set up our integral. And now I'm going to take a quick second to solve it. I'm going to kind of speed through this because I don't think the calculation of this integral is very hard and it'll kind of waste our time. But you're going to get that, you have 0 to 81. This is going to be the same thing from 0 to 81 of 9 minus x to the 1/2 dx. And then down here, you can just, I'm kind of get rid of that. This is going to be 9x and then minus x to the 3/2 times 2/3 on the bounds of 0 to 81. And then because these all have a term of x, you kind of cancel it out. So we just have 9 times 81 minus 2/3 81 3/2. So this will be kind of your answer. I'm not going to like solve that because it's going to take a little bit, but you can just plug it into a calculator and get the right answer. Okay. It's the integral from, there's no bounds, sorry, of 2x minus 5 times e to the x. Cool. And then dx. So this is going to be integration by parts. Question. Big rule of thumb is you never want to choose u to be e to the x. So we're going to choose this other piece right here, this 2x minus 5 to be our u. Integration by parts rule, by the way, I'm going to write it up here. The integral of u dv is going to be equal to uv minus the integral of v du. Okay, so we're going to choose u here to be 2x minus 5. That makes du 2 dx. And then that means we chose dv to be e to the x dx. And that means v is just going to be e to the x as well. Using this formula, we can say that this is going to be equal to u times v, or 2x minus 5 times e to the x, minus the integral of 2 e to the x dx, which is a lot easier to solve. We get this is going to be equal to e to the x times 2x minus 5 on the right-hand side, just kind of getting rid of the parentheses. And then we can say this is going to be 2 e to the x plus c. Is there any questions about how I got from one step to another?
Will we have to...
So this is going to be the integral of 4e to the 0.35x negative dx. Okay, so first of all, let's go ahead and pull this 4 out. So this is the same thing as a 4 from the integral of 0.35 negative x dx. And then we can use u substitution here. Because remember, this is one order higher than this x to the 0 that's imaginary on the front, right? So we can say u is equal to negative 0.35 x. The du is going to be equal to negative 0.35 dx, right? And then I can divide this negative 0.35, and I can say negative 1 over 0.35 du is going to be equal to dx, right? Now I can plug it in for dx. And I get 4 times the integral of negative 1 over 0.35 e to the u du. Now I can pull that 0.35 out. And then this will be times the integral e to the u du. And then you just get negative 4 over 0.35 times e to the u plus c And then you can just plug that back in for u, right? So you get negative 4 over 0.35 e to the 0.35x, negative 0.35x. Let's see. Cool. Okay, so it says we want to consider the interval 6x squared ln x dx. So it says if we use integration by parts where u is equal to ln x and dv is equal to 6x squared, what is du and dv? Du is just deriving, so du will give us 1 over x dx. And then v, sorry, it's asking for v, is just integrating the 6x squared, which we know will give us 2x cubed. Make a sip of water fast, give me a second. Okay. So now we have this, it wants us to solve the integral using part A. So we know this is going to be equal to u times v, or 2x cubed ln x, minus the integral of v du, which is going to be 2x cubed times 1 over x dx, which we can really rewrite as just 2x squared dx. We take the integral, and we get this is going to be 2x, sorry, it's going to be 2/3 x cubed. So we get this is going to be equal to ultimately 2x cubed ln x minus 2 over 3 x cubed plus c. So this integral from 0 to 1 of x cubed minus 10x minus 3 dx. Let's go ahead and find the integrand of this. It's going to be x to the 4th minus 10x squared over 2 minus 3x. Right? This 10x squared over 2 is going to become a 5x. And we can say this from 0 to 1. Okay? So we'll plug in 1 using the fundamental theorem of calculus. We'll have to plug in 1 and subtract when we plug in 0. So this is going to be equal to 1 minus 5 minus 3. And then we subtract 0 minus 0 minus 0. So what we really have on this side is we have 1 minus 8, which is just negative 7, minus 0, which is just going to give you negative 7. Recall, because we're using FTC, there is no plus c on this one. It's just negative 7. That's the area under the curve from 0 to 1. For f of x is going to be equal to x cubed, I think. Yeah, x cubed minus x squared plus 1 on the interval from negative 1 to 1 inclusive. We're going to find and classify the critical value, the maximum and minimum values of f on the interval. So in order to do this, we need to derive set it equal to 0 and then find all the critical points and then plug in what we found. We need to plug in those critical points to find to see if they're maximum minimums. We also need to plug in the interval bounds to see if those are absolute maximum or minimum. To visualize this and make this make sense, let's say we have this function from these two bounds, right? Or sorry, say we have this function, right, on these bounds. And it kind of looks like this. Even though there's a critical point right here, we observe that this is the local minimum, but it can't be the only absolute extreme because we see that the local maximum is actually at this point where the bound stops. All right, cool. So let's derive this real quick. All right, and we can also factor it. Right? This gives us the two solutions that x is equal to 0 and x is equal to 2. But we know that we can ignore the solution because it's not in the bound. So now we need to check these solutions for x and f of x of negative 1, 0, and 1. Negative 1, we get negative 1 minus 3 plus 1, so we get negative 3. Here we get positive 1, and then we get 1 minus 3 plus 1, which is going to be negative 1. Which means our absolute maximum is going to be at x equals 0, and our absolute minimum is going to be at the beginning of the boundary at negative 1. And that'll be your answer. Integral of x cubed plus 2x minus 3 over x to the 4th dx. I'd argue that you would you actually benefit from, wait. Oh, okay. Yeah, okay, so yeah, we are on target. I'd argue actually benefit from writing it like this, where we pull out this x to the 4th in the denominator as x to the negative 4th, and then we multiply all of our values by it. Which gives us, when you multiply them, you subtract powers. So we have x to the negative 1st plus 2x to the negative 3rd minus 3 to the negative 4th. And then this makes it relatively simple to integrate. So x to the negative 1st is going to be 1 over x. So this is actually going to give us ln x. Plus, we'll add 1, so it'll be negative 2. So x to the negative 2nd power. Then we have this 2 divided by that negative 2. So, okay. And then on this hand, this is going to be negative 4, sorry. Then we're going to have negative 3. So we have negative 3x to the negative 3rd all over negative 3. Okay. Plus c. And then we can simplify it a little bit. We get ln x minus 1 over x squared minus 1 over, plus, because these cancel out. 1 over x, 3x No, 1 over x cubed. There you go. Because these also cancel out. Plus c. Integral of x squared e to the 4 minus x cubed dx. I'd argue it's going to be u substitution problem, where we choose u to be 4 minus x cubed. Likewise, du is going to be negative 3x squared dx. And we're going to move that 3 over, and we're going to have negative 1/3 is going to be, sorry, times du. It's going to be equal to x squared dx. That's something we actually have in our function, x squared dx. So we can rewrite this function now as e to the u du. We can't forget about this negative 1/3 term that we have to tag out to the outside, giving us negative 1/3 e to the u plus c. And then we can plug that back in, and we get e to the 4 minus x cubed over 3 negative plus c.
How did you?
So considering the functions y equals 16 and y equals x squared, it's going to be our y equals 16, and then this is going to be y equals x squared. And we know this is going to cross at x equals 4, right? Because 4 squared equals 16. We want to know the area in between these two functions is right here when we sketch it. And then we want to set up an integral from 0 to 4 because we know this is our bounds. And then it's going to be the top function minus the bottom function. So 16 minus x squared dx. And then this is going to be 16x minus x cubed over 3 from 0 to 4.
But it doesn't say the first quadrant, so
It
is
doesn't. It
so like
doesn't
top
say
minus one?
the first quadrant. I see. Yeah. Yeah. No, you're right. You're right. Okay. Yeah. So for this one, let's expand it then. All right. So we have the line y equals 16. In this case, I'd argue it looks something like this, where this is still 4, but then on this side we have negative 4. So then this is really the integral that we want to calculate, which is the exact same integral, it's just a different bounds. Negative 4 to 4 of still 16 minus x squared dx, which is still going to give you 16x minus x cubed over 3 from negative 4 to 4. And then you can solve that yourself. D prime of p, right, is equal to negative 2000 over p squared, or negative 2000 p to the negative 2, right? Oh, p cubed, sorry.
Yeah.
Right, and you want to find d of 1000. So in order to get from the derivative function to the regular function, we know we have to integrate, right? So to find d of p, we need to integrate d prime of p dp, right? So it's just integral of negative 2000 p to negative 3 dp, and this is going to give you negative 2000, it's 20,000, sorry, over negative 2 of p to the negative 2, right? Which is going to be 1000 over p squared. Okay, let's see. And now we want to find 1000, right? Sorry, we want to know what happens when we have 1000 units, or d of 1000, which is going to be equal to 1000 over 1000 squared, which is going to be 1 over 1000, or 0.001.